Okay, kids, we're back, and we're going to talk about something today that is called escape velocity, escape speed. So we've got a graph here. What is this graph? This is a graph of universal gravitational potential energy along this axis here, and radius from the center of the object that is causing there to be a gravitational field. So you could think of perhaps the Earth, all right, is an object that's causing a gravitational field. And here is the graph right there. It's in red. That's what it looks like. And if you want to know what the function is, it's Eg is equal to negative. Remember, universal gravitational potential energy is negative. And we got big G. What's up, big G? The universal gravitational constant. In this case, we're going to use the mass of the Earth. Okay, it could be any object, Mars, the moon, what have you, but mass of the Earth in our situation. Mass of the object that is going to be moving through the gravitational field of the Earth. And when it's at that spot right there, its distance, whatever this object is, from the center of the Earth is the radius of the Earth. So along the radius axis, I'm telling you that right here is radius of the Earth. So imagine that there's an object sitting on the radius of the Earth. So we could pinpoint off this graph what its universal gravitational potential energy would be. We could actually calculate it right there, as I was saying. Let's, for the sake of argument, assume that this object is not moving. It's just you sitting there on the surface of the Earth. So your kinetic energy is zero. Your total energy would be the kinetic energy, which in this case is zero, and the universal gravitational potential energy right there. All right, and you could calculate it. We know what the universal gravitational constant is. We know the mass of the Earth is. Could be you. We know your mass, and we know the radius of the Earth. So that's the first situation. It's just sitting there. Let's change things up a little bit. Let's now say that instead of this object just sitting on the surface of the Earth, let's say it's been launched with a certain velocity. So let's say, I don't know, you shoot it out of a cannon straight up into the air, all right, or you launch it with a slingshot, or it's a soccer ball and Thor comes around and boom, kicks it, all right? So some ball being launched out into the air, all right? So what's its total energy? Well, ET is equal to the gravitational potential energy that the object would have. You would calculate it in exactly the same way. All right, we're not going to launch you, so the mass of the object might be different. Let's say we're launching a ball, okay? And it's kinetic energy. And we could then substitute in the equation, right? There it is for universal gravitational potential energy. Don't forget the negative sign. And we would add to it its kinetic energy, the standard equation for kinetic energy. So take a look at that for a second. So what happens is, let's say it's something that shot up straight into the air. So as it shot up into the air, its distance r from the center of the Earth increases. So that means you're getting a bigger and bigger and bigger and bigger denominator, all right, which makes this a smaller and smaller negative number. But being smaller negative actually means EG is increasing. What I'm trying to tell you is that -1 is larger than -3. You have to continue that pattern along the number line. 5 is larger than 3, which is larger than -1, which is larger than -3. Let's go back to the graph for a second. Okay? As R gets bigger, the function becomes less and less negative, so it's actually increasing. You kind of got to wrap your head around that a little bit. So let's get back to what we're saying here. As R increases, the universal gravitational potential energy increases and the kinetic energy decreases, which kind of makes sense. As you shoot something up into the air, we know if you throw something up into the air, as it's moving upward, its kinetic energy decreases. All right, so kinetic energy is decreasing. We have the law of conservation of energy that tells us that the total energy is constant, right? the total energy being universal gravitational potential energy and kinetic energy. So as kinetic energy decreases, some other energy has to increase, and it's the universal gravitational potential energy. So let's pretend that eventually, at some point, right, r equals infinity, at r equals infinity, this is what's going to happen. The kinetic energy decreases so much that if we could get to this place called mathematical infinity, its velocity would be zero, and therefore its kinetic energy would be zero. So think of shooting an object off the surface of the earth. It fires away, leaves the surface of the earth. As it's gaining altitude, it slows and slows and slows and slows and slows. Kinetic energy keeps on decreasing. Well, eventually, it's going to slow so much, its kinetic energy is zero, its velocity is zero. Where do we say that happens mathematically? Well, we say that happens at r equals infinity, wherever that may be. Remember, these are all mathematical constructs. So what scientists, physicists have said is if you have escape velocity, so with escape velocity, it defines escaping Earth is defined as reaching infinity, and at this point, r equals infinity, gravitational potential energy is equal to zero. Because if you put, let's go back up into here, if you put an infinity into here, if you could do that, this whole quotient fraction would become zero, because as this denominator approaches infinity, as it gets bigger and bigger and bigger, the entire thing approaches zero. So what we're saying now is, by definition, if you are shot off the surface of an object like the Earth, you're going to escape it. Escaping the Earth is defined as reaching infinity, and when you reach there, gravitational potential energy is zero. Thus, two things are occurring here at infinity. When you get to r equals infinity, we're saying Eg is zero, but a few moments ago we said when you get to infinity, it slows down to zero, so therefore its kinetic energy is zero. So two things are happening if you have escape velocity at r equals infinity. Your gravitational potential energy is zero, and your kinetic energy is zero. So in terms of that sum, in terms of the total energy, so in terms of total energy, an object must have a total energy equal to zero for it to escape, or for it to have an escape velocity. If an object has escape velocity, it means at r equals infinity, its gravitational potential energy is zero, and at r equals infinity, its kinetic energy is zero, or therefore its total energy is zero. Its total energy is zero. But remember, total energy is conserved, which means it would have to have a total energy equal to zero during its entire motion. Total energy would have to equal zero. Total energy would have to equal zero, and that's what I'm saying here. For an escaping object, all right, for an object to escape the Earth in our example, or any object, all right, it has to have a total energy equal to zero. And this must be true everywhere, including when it was being launched, sitting there being launched into the air at Earth's surface. So at r equals infinity, when it's on the surface of the Earth and it's being launched to escape, if it escapes the Earth's gravitational pull, by definition, this has to be zero. It's being shot up fast enough so it can leave the Earth's gravitational pull. Having ET equals zero literally defines it has enough total energy to escape. That's by definition. So we put in the equations here, right? Negative g, remember this quantity is always negative, mass of the Earth, mass of the object. It's sitting on the surface of the Earth, plus its kinetic energy when it's on the surface of the Earth, which is half mass of the object, v squared. So it's going to be launched at some velocity v, which we don't know yet. But when you add these two terms, it has to equal 0 if this object is going to escape the gravitational pull of the Earth. So we cancel out the mass of the object, right? We bring this term over to the other side. We bring this term to the other side, and we multiply it by 2 to clear the half. So try to work through getting from here to here. I've canceled out mass of the object. I've brought this term to the other side, and then I've multiplied both terms by 2 to clear the half. And we end up with this equation right here, okay, which I can then square root. I can then square root. And if I put in 2 times universal gravitational constant times the mass of the Earth, all divided by the radius of the Earth, and then I square root it, I get this quantity right here, 1.12 times 10 to the 4 meters per second, or 11.2 kilometers per second. Which means if you are launching an object, your Thor comes around and boots a soccer ball, okay, boom, if you want it to leave the gravitational pull of the Earth, if you want it to escape the gravitational influence of the Earth, it must be launched at 11.2 kilometers an hour. This is the velocity which matches up with total energy equal to 0. That's why it's called escape velocity. That is why it's called escape velocity. You can calculate it for any object. If you want to know how fast you got to launch an object to escape from any object, so any mass can go here, when you're at any distance from the center of that object, here's the equation. So let's say, I'm some satellite that's going around the sun at some distance, some orbit from the sun, and now I want this satellite to escape the sun. Well, you would put in the mass of the sun, G2, and where is it right now? How far away is it from the center of the sun right now? Okay, you know that? Plug that in there. All right. If you want it to escape the gravitational influence of the sun, boom, you calculate V. That's how fast it's got to be booted, launched from that orbit radius for it to escape the sun. That's what has to happen. Now, these calculations are for something that is launched. It's not for a rocket which has a continual force being put into it. That's a different calculation. All right. That means the force keeps on going, keeps on pushing, keeps on pushing. No. This is if you just give it that one quick impulse and boom, we want it to escape. So please don't confuse the two. So what does this look like graphically? Well, let's graph total energy, which I'm going to have in red in these three situations. Gravitational potential energy, which I have in green in these three situations, and kinetic energy, which I have in blue in these three situations. So take a look at the graphs here, because I'm graphing energy along the vertical and R along the horizontal, how far the object is that's being launched is from the center of what is creating the gravitational field. Okay, I trust you paused the video and had a look at this. So when total energy is 0, look, red line is along the 0 line for energy. Here's energy, positive energies, negative energies, 0 energy. Our total energy is 0. What does the graph look like? Well, here's the gravitational potential energy, and here is the kinetic energy. So picture an object that's maybe on the surface of the Earth. Boom, it's launched. Well, as it goes higher and higher and higher, it slows down. And as it slows down, as it gets higher and higher and higher and higher, the gravitational potential energy increases. All right, until you would get to infinity. But they're approaching infinity here. So gravitational potential energy here is approaching 0. Here, kinetic energy is approaching 0. This is the graph for when you have enough velocity that it escapes in this example, let's say the Earth, okay? And when it gets to infinity, it'll stop. That's what this graph is. If you've got a total energy greater than zero, it's very similar. Here's the total energy. It's above, here's zero line for energy. So the total energy is zero. It's above it. So let's say you launch an object, boom, off the surface of the Earth. Let's use the Earth again, all right? So as it leaves the surface of the Earth, it slows. Its kinetic energy is decreasing. It's approaching not zero now, it's approaching this value, all right? And the gravitational potential energy still approaches zero. Well, what does this mean? Well, this means that when you would eventually get to infinity, wherever that is, you wouldn't be moving at zero there. You would have actually some velocity there. That's the difference between these two. Here, you launch an object with the minimum speed to escape the Earth. We always use the Earth as an example because we live on it. So when it does get to infinity, its velocity is zero. Here, boom, you launch an object, let's say from the surface of the Earth. When it gets to infinity, it still has velocity. You've got more than it is needed to escape. Escape velocity is the minimum velocity needed to escape. Here, you've got more. Let's continue this. Let's say we're going to launch an object off the surface of the Earth, all right? But now the total energy of the object is less than zero. So what happens is, boom, you launch the object, it slows until kinetic energy gets to here. And here the kinetic energy is zero and it stops. So as it was being launched, the gravitational potential energy would increase until it gets to here. And then we stop graphing. We stop graphing here because the object stops. The object stops. It doesn't get any further away. It would eventually fall back downward, right? It would fall back down, not escaping. So we have three situations. Escape, just escapes the gravitational influence of the Earth. When it gets to r equals infinity, it's at velocity zero. Here, escapes the gravitational influence of the Earth, and when it gets to r equals infinity, it has a velocity greater than zero. Total energy less than zero, we launch it from the surface of the Earth, and in the example we're using, it climbs, and then it stops. Kinetic energy is zero. It never escapes. So these are the three main situations that can be investigated when we're talking about escape velocities. So this whole discussion about escape velocity has led scientists to come up with an idea called binding energy. The binding energy of an object is the amount of kinetic energy that has to be added to any object so that if you add this kinetic energy, its total energy will be zero. How much energy do we have to add to an object in a gravitational field, universal gravitational field, so that we can get its total energy to zero? That's what this means right here. So let's do an application of this. Let's say we've got an object that is in orbit. Once again, we'll use the Earth. Let's say that you got some satellite rotating, orbiting around the Earth, and we want to apply the whole idea of binding energy to it. Let's do that. Okay, well, here's something that's kind of familiar to you. You've done this. We're going to use the Earth as an example. Satellites moving in a circular orbit. Let's say this is the Earth, and here's a satellite, and it has a certain mass, ms, mass of the satellite. There it is, and it's undergoing uniform circular motion right there. So we know that the net force acting on the satellite is equal to the mass of the satellite times its acceleration. We know that the only force acting here is universal gravitation. And we know that this particular acceleration is centripetal, so we can put v squared over r in here. R being how far the satellite is from the center of the Earth. It's always center to center distances. So let's put in what universal gravitation is, big G. What's up, big G? Mass of the Earth, mass of the satellite, all over how far it is, right? Center to center, r squared. And over here we have mass of the satellite, how fast it's moving squared, and r again, how far it is from the center. So what we have here is a canceling of some r's going around, right? There's an r here and an r squared there, so we cancel out that r and we're just left with mass of the satellite over times its speed squared. And over here it goes from r squared to r. All right, so this we've done before. This is all the whole uniform circular motion, centripetal acceleration work. So we've done this before. But now let's take a look at what energy it has right here. So its total energy there is equal to its kinetic energy plus its gravitational potential energy, universal gravitational potential energy. So that would equal half the mass of the satellite, v squared, times negative g, mass of the Earth, mass of the satellite, all over r. Remember, universal gravitational potential energy is a negative. So let's take a look at this term right here. Mass of the satellite times v squared. Look at that. Mass of the satellite times v squared. Oh, look, I know what that is right there. So I can take that and plug it in here. So the half stays, and now I've got g, mass of the Earth, mass of the satellite, all over r. All right. Well, I got half of a positive term here and a whole negative term. Look, they're identical. GG. What's up, GG? Mass of the Earth, mass of the Earth, mass of satellite, mass of satellite, and in the denominator, it's an R. So they're the same term. I have a negative whole and a positive half. What does that leave me with? A negative half of it. So the total energy of that satellite in orbit is negative g, mass of the Earth, mass of the satellite, all over 2r. So getting back to what we started with here, the binding energy. How much kinetic energy would we have to give to that satellite so its total energy would become zero? Well, if you want this term to be zero and it's now negative by this amount, if you want it to be zero, you just add the positive version of that. And when you would add these two together, you would have a total energy equal to zero. So this positive amount that you're going to add is called the binding energy. That's how much kinetic energy you would have to add to it for it to get to a total energy equal to zero and therefore escape. So what would the kinetic energy be? It would equal this amount right here. And we know that that is equal to half mass of the satellite v squared. So let's take look at these two terms here. Mass of satellite cancels, the halves cancel, and we have g, mass of the Earth, all over whatever radius this satellite is from the center of the Earth equals v squared. So this is how much velocity or speed we would have to add to the satellite that's in orbit right now in order for it to escape. We would have to add this velocity speed to the present speed it has for it to escape. This is the whole idea of binding energy. All right, then that's today's lesson, kids, all about escape velocities, total energies being equal to zero, binding energy. Take your time with it, read the textbook, slow down this video if you have to, and I will give you some questions to work on this last part of this section in chapter 6. Take care. Be safe. Be safe. Be safe. I know you miss your friends. Okay. And we'll talk to you later. Bye bye.